All right, guys, in this video, we're going to cover graphing polar. Although you don't explicitly have to graph polar on the AP exam, you really need to understand the polar graphs, because what we're going to do in the next section is we're going to find the area of these polar graphs. And the hardest part of the area is to come up with the bounds. Okay, so for example, if they asked you to find the area of the, let's say, one petal here, most important is where this graph leaves the pole and then enters the pole. So we're going to integrate from, let's say, 0 to pi over 3. If they ask you to find of the 3 petals, we might do symmetry and do 3 times and do from 0 to pi over 3. And these can get more complicated, so maybe they want us to do, let's say, an inner loop like this, and then we'd have to find the area of, let's say, just that part of the loop. So it's really important to understand where a graph, exits the pole, enters the pole, exits, and enters the pole, and stuff like that. So I'm going to give you a couple ideas of how to do this. There's no one right way to do it. It's really not important that you understand like what a rose curve is or a cardioid. Like I think when you guys did it in pre-calc, that's how you did it, but that's not really quite as important here. It's really just figuring out, like I said, the entrance to the pole and the exit to the pole, because that's going to oftentimes be our bounds. Okay, all right, so what I'm going to do first is I'm going to give you a couple of shortcuts, and then hopefully you understand, and then you can just kind of, create your points. It's really creating the points so you can figure out where it's equal to 0. A lot of times that's where we're going to put our bounds. Okay, so for example, here we have 6 sine of 3 theta. So the 6 is not a big deal. It just means that the sine curve is going to go from 0, instead of 0 to 1, 0 to 6, back to 0 to negative 6, 0, 6, 0, negative 6, and so forth. So let's not worry about the 6 part of it. It's really the sine of 3 theta. So if you were to graph this, when we do the sine curve, we do 0, pi over 2, 3 pi over 2, 0, pi over 2, pi, 3 pi over 2, 2 pi, right? So those are our sort of key points, right? So we would say pi over 2, so we go 0, pi over 2, pi, 3 pi over 2, 2 pi. So that's like a full cycle. And again, it could go up to 1, it could go down to 1 or 6 or whatever. That's not the important part of it. The important part is going to be the theta values. So if I have sine of 3 theta, I know that I need to set the 3 theta equal to pi over 2, because those are my normal increments. So if we set the inner piece here, so 3 theta equal to pi over 2, we get theta equals pi over 6. So watch. So this first one is pi over 6, which should make sense, because if you plug in pi over 6 to this, we're going to get pi over 2. The sine of pi over 2 is 1, or in this case, because of the 6, it's going to be 6. Then this, so we're going to go in increments of pi over 6. So then this is 2 pi over 6, 3 pi over 6, and 4 pi over 6. So that's one cycle of the sine curve. Now sometimes you're going to have to go further, which is fine. But let's see. So if I plug in 2 pi over 6, which is really pi over 3. So if I plug in 3 times pi over 3, I get pi, which makes sense, because at pi it's 0 and so forth and so on. So you could do it using the graph, or you can use it using the chart. I like doing the chart just because it's relatively mechanical. But you could start your graph here. So what's really important, I think, for the Calc 2 aspect of this is to graph where it's equal to 0. Okay? Because these are going to be where the graph enters the pole and exits the pole. So I like to just draw them as little asymptotes. Okay, so at 0, I drew. This is 2 pi over 6, or pi over 3. And then 4 pi over 6, which is 2 pi over 3. Okay? And then another thing to note is, so if we were to graph this, we'd start at 0, it's 0. At pi over 6, it's at 6. So we come out to 6, and then it goes back into the pole. So that's important. So that means my bounds for this area would be from 0 to pi over 3. Now, when a graph enters, so it's exiting the pole, then it enters the pole, is it always comes out along the same asymptote. So since it's here, we're going to continue, we have to come through this way on the pi over 3. right? So we go back in here at 5 pi over 3, so we come out on the 5 pi over 3, or the 2 pi over 3, okay? So let me just kind of go over this chart here, and you pick whichever works for you. So what I would do for all of this is first set, it doesn't matter, either figure out where the asymptotes are. So to figure out where the asymptotes are, without doing the graph, we can just simply set the r equal to 0. So that's what I did here. So I set r equal to 0. So when is the sign equal to 0? Well, at 0, pi, and 2 pi. So then I said, well, 3 pi equals 0, 3 pi equals pi, 3 pi equals 2 pi. So we got 0 pi over 3, 2 pi over 3, which is what we got on our graph. I'm just not doing it with the graph. So I'm going to draw asymptotes at 0, pi over 3, 2 pi over 3. Okay, and then I'm just going to go ahead and start picking some points. So what I like to do is I'll start with this column here. It's kind of like setting this equal to pi over 2 is really what I'm doing, because when your key points are at 0, pi over 2, pi, 3 pi over 2, and 2 pi. So I did 0, pi over 2, pi, 3 pi over 2, 2 pi. That's a full cycle of the sine curve. But it's 3 pi, right? So I have to divide out the 3. So it's going to be at 0, pi over 6, pi over 3, pi over 2, 2 pi over 3. That's a full cycle. So it goes 0, 1, 0, negative 1, 0. Since we have the 6 in front, it's going 0, 6, 0, negative 6, 0. So that is a full cycle. So let's see if we can graph that. At 0, it's 0. At pi over 6, it's at 6, and it goes back to 0. Now that might be enough for the calculus part of it, because even if we needed 3 petals, so this tells me the number of petals if it's odd, and then I could find 1 petal, multiply it by 3. But let's just keep going. So then at pi over 2, it's at negative 6. So then we come out to here, and then we go back into the 0, which is why I kept going down here to complete this, okay? So we got all 3 petals, okay? So again, totally up to you. So the 2 things that I would suggest is to set the inner part equal to pi over 2. That will help you with your key points on your graph, so like these. And then I think it's really important that you set the whole thing equal to 0, because that's going to give us, yes, it's the zeros on the graph, but more importantly, it's the asymptotes, and it's where the graph enters and exits the pole. All right, so let's see for the second one. So it's a pretty basic function here. So again, you want to start with, so this one we don't have to set the inner part because it's just theta, but you're basically saying, you know, theta equals to pi over 2, and then you're going in increments of pi over 2, which is normal, right? We do 0, pi over 2, pi, 3 pi over 2, 2 pi. Okay, we have that down. Then we're going to set it equal to 0. So sine is equal to 0, 0 pi and 2 pi. So this one's a really basic function. I don't know if any of you remember, but the sine is on the y-axis, the cosine is on the x-axis. So we're just graphing on the y-axis, and we're going out to 3. So it's going to go 0. Instead of 0, 1, 0, negative 1, it's going to go 0, 3, 0, negative 3, and 0. Okay? So at 0, it's 0. So this is your asymptote right here. I didn't even draw it. I don't even know if it was necessary to draw this. For that one, okay? So we've got at 0, it's 0. At pi over 2, it's 3. And then at pi, it's back to 0. And then 3 pi over 2 is negative 1, so it's back up to here. Or in this case, negative 3. And then at 2 pi, it's back to 0. So we just got a little circle type thing up above the x-axis for that, okay? All right, so here we've got 4 petals. So when it's even, see how it's even, the 2 theta? That means it's 2 times, so your petals is like, they say 2n. So it's 2 times 2, which is 4. If it's 3 theta, then it's just 3 petals. Okay, so it tells me I have 4 petals. So again, symmetry is great here. You could do 1 petal multiplied by 4. Maybe they just want the 2 in the first 2 quadrants. It really just depends. But again, we're going to start with, I'd start with the 2 theta equals pi over 2. Because when you were to, if you were to graph sine curve, Let me just do it. Hopefully you're understanding this a little bit better, but when you graph the sine curve, it goes pi over 2, pi, 3 pi over 2, 2 pi. Those are my key points. So we go 0, 1, 0, -1, 0, like that. So if I do 2 pi, or 2 theta equals pi over 2, I'm going to get theta equals pi over 4. So let's see if that makes sense. So that means my increments are going to be pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4. So this is pi over 4, pi over 2. So if I plug this back in, so if we did sine of 2 theta, if I plugged in pi over 4, I'm going to get sine of pi over 2, which is 1, which is that point right there. Okay, so we have to account for that multiple on the inside. So that's one little cycle. That's probably going to give me 1 petal. Okay, so let's see what happens here. So, and then you also want to set it equal to 0. I don't think I did that yet. Yeah, so let's set that equal to 0. So sine of 2 theta equals 0. So we know that sine equals 0 at 0, pi, and 2 pi. So 0 equals 2 theta, pi equals 2 theta, and 2 pi equals 2 theta. So theta equals 0, theta equals pi over 2, and theta equals pi. So you'll see here I drew, so through the 0, which is also pi, and then pi over 2. All right, so let's start. So I went in increments of pi over 4. So you can start this column with your normal increments. So 0, pi over 2, pi, 3 pi over 2, 2 pi, and work backwards to get to here. So you're not going to do both, and that's what just to be clear, you're going to either do it this way or you're going to do it this way. Do not do it both. Okay, so all we're concerned about is the 0 and the pi over 2. That's what we care about. And you can see it here. It leaves the 0, it enters the 0. So it's 0 and pi over 2. Those become our bounds when we integrate. Okay? So again, I'm just going to plug in. So this is going, so 0, 1, 0, -1, 0. And then same thing, 1, 0, -1, 0. So those are my cycles. And again, you could stop at any point that you can pick up the pattern to this. So I probably, honestly, 0, 1, 0, -1 would have stopped right here. Okay, so at 0, it's 0. At pi over 4, it's 1, and then it's back to 0. So it entered in on the pi over 2, so it's going to exit on the pi over 2. And then it enters back in on the 0, so it's going to exit on the 0, and so forth and so on. Okay, then you can come up with all your points if you need to. Okay, but again, it's this or it's this. Do not do both. Okay, because again, you're not going to graph this on the AP exam. You're just going to try to find the bounds to be able to find the area. Okay, all right, so let's look at this one. 3 theta, so again, we're looking at 3 petals. We're going to set, first set it equal to 0, so I did that down here. So cosine of 3 theta equals 0. We know cosine equals 0 at pi over 2 and 3 pi over 2. So we do 3 theta equal to pi over 2, 3 pi over 2. Again, I'm just going to make a point again. So we have -2 cosine of 3 theta. We know that the cosine graph goes from there to there to there to there to there. So that's what I'm looking at. So this is normally pi over 2. This is pi, 3 pi over 2, and 2 pi. So let's see what happens here. We're saying theta is pi over 6. I'm going to go in increments of pi over 6. Yeah, so if this is pi over 6, let's see if that works. If I plug that back in, we're going to get cosine 3 times pi over 6, which is cosine of pi over 2, which is 0. Okay, so all we're doing is we're kind of keeping the curve the same, but going in and adjusting the key points. Okay, so we're going in pi over 6. So again, I like to do the chart. So if you notice here, the chart, I've got my normal increments in this column. So it goes 0, pi over 2, pi, 3 pi over 2, 2 pi. That's one cycle. And then I divide out the 3 to come over here. And then these are going to be the points. So this is because of the -2. We know cosine goes 1, 0, -1, 0, 1. That's my full cycle, but the -2 on the outside is going to change the height of it, right? So it's going to go, instead of up to 1, to 2, and then instead of down to -1, down to -2. So we're going to start at 0, it's at -2. So at 0, we're going to be at -2. So we're over here. And then at pi over 6, we're at 0. So I start here, and then you're going to come back in here. Now we have to exit on the pi over 6, like this, which pi over 3 puts me at 2. So you get there, and you sort of just keep circling around like that. And that finishes it. Okay, so again, is you can stop, and you're going to see you're not going to really need to do all of this on the AP exam. Because a lot of times they'll just ask you in the first quadrant, or maybe the first and second quadrant. It's very rare that they ask you for all 4 of the quadrants, okay? But it's really hard for students to come up with the bounds. So I just think the better you can understand the graphing, it'll help you with the bounds, okay? So again, if we started off, this is where it's equal to 0. Look at where I have my asymptotes. So we have pi over 6, pi over 2, we probably need one more because of the 3. So let me see this for a second. So we know cosine 3 theta equals 0. So we know that cosine equals 0 at pi over 2. So 3 theta equals pi over 2. 3 theta equals 3 pi over 2. And then we're probably going to have to go one further, right? To that one. So sometimes you're going to have to go further out because of the 3. We're dividing it by the 3, which allows us to pick sort of a larger value, right? We're actually going past the 2 pi. Okay, so at 2 pi, so 2 pi plus pi over 2 is 5 pi over 2. So 3 theta equals 5 pi over 2. So we get theta equals 5 pi over 6, which is my other asymptote here. Okay, so I've got my 3 asymptotes, and then we just start with the points. And then once you get the feel of the graph, you're going to use symmetry a lot for this. Okay, so we're going to say I start with at 0, we're at -2. And then at pi over 6, we're at 0. So we come back in. Then at pi over 3, we're at 2, and then we come back in. So you could actually integrate this here. So we'd actually integrate from pi over 6 to pi over 2. Hopefully you can see that. So pi over 6 to pi over 2, that's 1 petal. That would allow us to find the area here, and then if we needed all 3 petals, we could just simply multiply it by the 3. All right, keep going here. This is very tedious, which is why I opted for the completed notes. But again, same process. Asymptotes and the zeros, most important part of this, okay? So I'm going to start with setting equal to 0. So it's at 0 at 2 pi over 3 and 4 pi over 3. So you might need to add that in to your chart because it's really important to get those zeros, especially for these inner loops. So I graph this. So 2 pi over 3, 4 pi over 3 we're going to start with, okay? Then again, it's just 2 cosine of theta, so again, not a big deal. Instead of going out to 1, you're going to 2. -1 is -2, that's the 2, not a big deal there. And then the cosine, theta is not altered here, so we're doing 0, pi over 2, pi, 3 pi over 2, 2 pi. So if you notice here, I did 0, pi over 2, pi, 3 pi over 2, 2 pi. I just added these in to get the zeros. Because of this 1 here, the 0 is not falling on the normal increments of it because it's sort of a shifted graph, right? Think of the graph on a rectangular plane. On a rectangular plane, this is the cosine graph, twice as fast, but shifted up 1 unit. So normally it's, it's here, here, there, there, there. No, I take it back. Not shifted up. Shifted up. Did I say 2 or 1? It's shifted up 1 unit, okay? And the 2 is simply just meaning that it's going to be, instead of at 1, it's going to be at 2. Here, -2, 0, 2. So it makes it a little bit quicker. like that, and then we're going to shift all of that up 1 unit, okay? So the 0 changes, okay? It's not on our normal 0 pi over 2 pi, 3 pi over 2, and 2 pi. We just set equal to 0, so I get these two values here for theta. So I draw this. So I'm going to go ahead and just plot my points. So we're picking 0. Cosine of 0 is 1. Plug it into the function, we get 3. So at 0, we're at 3. So that's this point right here. Then I go to pi over 2. So at pi over 2, I plug it in. Cosine of pi over 2 is 0. And then so we get the 1. So at pi over 2, it's at 1. So you start here and you come back to there. Okay? And then we go at 2 pi over 3, we go to 0. That is so important, because a lot of times you're going to find half of the loop. So we start at 3. So you could actually find, if this inner loop wasn't here, let's say, we could actually go from here to there. So my bounds would be 0 to 2 pi over 3 would give me all of this area. And then we would use some sort of symmetry going forward, okay? So we've got 0 to 1 back to 0. Then at pi, it's at -1. So instead of being here, it's going to be here. That's where my inner loop starts. So at pi, it's at -1. So it's here. And then, what do we got? At 4 pi over 3, which is here, it's back to 0. Because a lot of times they'll ask you for the area of the inner loop. So we want to figure where we enter the loop and where we exit the loop. So we entered it at 2 pi over 3. We exited at 4 pi over 3. For those of you that are creative, we're going to say, well, I'm going to just do half of the loop. So 2 pi over 3 to pi, then double my area. But again, it's all about the bounds. Okay? All about the bounds. So then we enter the loop. We exit the loop, 4 pi over 3. And then, so at 4 pi over 3, we're at 0. And then at 3 pi over 2, we're at 1. And then we come back out like this. So again, depending on the question, they might ask us for the area of the inner loop. They might ask us for the area of the whole thing minus the inner loop. So again, and you'll see that the area overlaps itself. And we'll address that in the next video, but it's important to understand the bounds. That's why I like the chart, because really when I zoom through this chart here, what I'm really looking for are the zeros. And that sort of sets my bounds most of the time, okay? All right, same idea. And again, is this one cosine? So it's on the x-axis. This one is sine on the y-axis, okay? So I'm going to start with setting it equal to 0. So we've got, I don't have my work here, but we've got 1 plus 2 sine of theta equal to 0. Sine of theta equals -1/2. So it equals -1/2 at 7 pi over 6 and 11 pi over 6. And these are my asymptotes. And then there's nothing affecting the theta here, so we can just go with our normal 0, pi over 2, pi, 3 pi over 2, 2 pi. But what I like to do is put back in the asymptotes here. So all I do is insert them in. If these weren't here, this would just be my normal sine curve, right? 0, pi over 2. I added this in just for graphing purposes. But, so at 0, I plug into here, I get 1. So at 0, we're at 1. And this one's interesting to find the area on, because it's almost like you have to go negative pi over 6 to start this. Like if you wanted to do half of this, we'd probably do negative pi over 6 to pi over 2. But again, we got a lot to work on with the area. That's a whole nother can of worms. But we start with the 1. Then at pi over 3, it's at 2.7. At pi over 2, it's 3. So we start here. We go out to there. And then at pi, it's at 1. But then we go back in here. Because that's important. Where you enter the pole. Okay? So we're looking at 7 pi over 6. Now for the inner loop, this is really important. So we enter the inner loop at 7 pi over 6. So if they just wanted the area of the inner loop, you're only going from 7 pi over 6. So 7 pi over 6. And then you're going to exit at, I believe, 11 pi over 6, right? So we enter at 7 pi over 6, exit at 11 pi over 6. So if you were to integrate that, our two bounds here would be 7 pi over 6 to 11 pi over 6. So again, that's why you really need to understand this. Although you don't have to graph it, you're going to have to come up with the bounds. And that's the whole point of these FRQs, is to find the area. We need the bounds. Okay, so enter, exit, and then we complete it. Okay? All right, you guys, that's it for this video. Hopefully with practice, you'll feel more comfortable. Just pick a way to do it. You can either do the chart or you can do the graph. The reason I like the chart is I don't know, it's very mechanical. And then I sort of just scan this through. You're really looking for the zeros here because from my experience, most of the time it's going to have to do with where a graph leaves and enters the pole is where we're going to get our bounds to once we start finding the area, which is in 9.5. All right, you guys, let me know if you have any questions. Please come see me if you don't understand anything. Thank you.